Good afternoon, everybody. Thanks for calling in. Today, I want to talk a little bit about a very detailed design aspect of some of our parts that we do very well. I think we do it better than some of our competitors in some of our core part strategies, and going back several decades of Eagle Bergman designs. And that is something that seems very simple, but it's not. And that is how pins make contact with their holes, their slots, what have you. And here I kind of show a graphic just to kind of put you on the roadmap. This is the cross section of the pin. It could be a drive pin, it could be an anti-rotation pin, doesn't matter. And it's inside this hole. So this is the corresponding hole that it's either driving or preventing from rotating. And this material just kind of extends to wherever. And you'll have some sort of force on the pin, between the pin and the pinhole material or the slot. And since you have contact there, you're going to have some sort of stress field. And so over to the left, this guy right here is Heinrich Hertz. Of course, he was a good German citizen from Hamburg, and he was critical in some of the German and Austrian industrial revolution, where engineers started studying machine elements like gears, gear teeth, pulleys, bearings, a lot of these steel machine components that we knew how they work, but we didn't really know how to design them or make them last longer, or what materials to make them from. So Heinrich Hertz started studying these stresses between two contacting machine elements. And they could be gears, of course, bearings, and then in our case, pins that are contacting the side of a pinhole. And he studied these elastic deformations and came up with, and ultimately what was named for him was the Hertz contact stresses. And the Hertz contact stresses are stresses that develop between two elastic bodies, like here. And you can see right here, I've drawn a representative stress field. And this is stress, that subscript C is contact. And you can see if we had this cylinder and it was contacting inside this cylinder, and these two bodies were perfectly inelastic, meaning infinitely stiff, their point of contact would be a perfect line, and a line that would exist along the length of the contact zone. Well, if you have a line has no area. And since stress is force applied across an area, if that area is zero, then essentially you would get infinite stress along that contact line. And we know that that's impossible and impractical. So since these are elastic bodies, once they're under force, they will kind of contact into this. Some people refer to it as a contact patch. Some others refer to it as the Hertzian area. Others refer to it as the elastic net area. But you get it. Contact patch is certainly the easiest way to understand it. And so, first of all, how do you understand what area is going to develop elastically between these two materials? And then once you have the area, you have the resulting stresses. And this is something that Hertz studied quite a bit. And this came to be called Hertzian contact theory. And pure Hertzian contact theory assumed that these stresses were all below the elastic limit of these two materials, meaning neither of these materials is going to be permanently deformed. So that is elastic stress, meaning once the force is removed, both will return to their original shape. It also assumes that there is no friction between these two materials. And of course, as engineering evolved, a lot of the models took over and said, okay, well, we know there's probably going to be some relative motion. Once you got into the design of bearings, then of course you have relative motion. And so basically there is no tangential interaction between these two surfaces, nor is there any longitudinal action between these two surfaces. This is just a beautifully elegant contact between two elastic bodies. So what does this mean to us? Well, if you look at the next and final slide, this is kind of something I put together. And let me explain what's going on here. On the x-axis, what we have is the ratio between the pin diameter, little d, and the hole diameter, big D. And then on the y-axis, I have what's called a stress factor. And that just means as I go from whatever stresses I were to calculate based on the materials and the actual diameters and everything else, it would go from 1 and then up to a stress that would be 10 times that as we move down the x-axis. So here, you can think of these as just the ratios. In this case, you have a pin that just fits into a hole. And so in that case, little d over big D, that ratio is going to be 0.9. Now, as I keep the pin diameter constant, but what I do is I'm increasing the hole size. Here, the hole size is twice the diameter. Well, a ratio of 0.5. Here the pin is a diameter ratio of 0.2, and then eventually this diameter becomes so big that you consider it to be an infinite plane. And so as this ratio goes up, you can see the stress factor. I keep wanting to say fracture because I'm so used to saying it. Stress factor will go up non-linearly. This is not parabolic. It's actually kind of a complex. I think it's like a second or, well, no, I think it's like a third order equation. But you can see somewhere it's fairly linear up through, 0.5, 0.4, 0.3. Right around 0.2 is where the stress factor tends to exceed 5 and then climbs up quite high as you approach a perfect plane. So right around here, about this 20% number, 0.5 is kind of a good design number. This is 0.9. You look and say, well, that looks like the lowest stresses. That's true, but then you get into some positional tolerancing that can be a little bit funky. The other thing is, once you're down into this 0.9 ratio, this contact patch area becomes so big that it's almost impossible to say that there's no relative motion or fretting between the two. Okay, so you'll see that, and this would be kind of typical of for example, on the SH seal on the carrier, you have holes through which the anti-rotation pins extend through, and this would kind of be typical of that. So that's why some of those parts are have such high tolerances and are controlled positionally so well. And that's to minimize these stresses, which again will minimize fretting, bending of the pin, that sort of thing. Now, as you go up to 0.5, what you're into here is probably something more like a flexibly mounted seat, which has a pin slot in the face and then a pin that extends through it as an anti-rotation mechanism. And here you can see that stress factor has maybe doubled. But again, you have that flexibly mounted O-ring that's going to accept a lot of that stress as well. And some of the flexibly mounted O-rings, this is one of the reasons that the pressure is limited. Not just shear damage to the O-ring, but also the internal stresses, the elastic stresses between the anti-rotation pin and the slot. Here you can go up to something that's fairly ridiculous. I can't think of anything used in mechanical seal design that will look like this. And what you would see is those that contact stress, those Hertzian stresses would get considerably high, higher than you would just calculate as a bearing stress field. And so, and what you're doing is it's getting closer and closer to that infinite line load. And then you can see this stress factor is going up, maybe 10 times that of the SH type design. On this, you get in some of the low duty seals of our competitors. They do this because it's fairly easy, and the load is not going to be so high that the stress factor is going to be that high. Because remember, these loads are typically developed by face friction. And if you have a face friction load that's so high that it's going to inelastically deform this pin, then probably the seal is going to fail from dry running or some other aspect. So you do see these. If you can tell what I'm doing here, if you had a flexibly mounted seat and the hole or the milled slot looking down on it looked like this instead of this, then you would get this planar contact. And so the stresses at the contact patch are going to go up a little bit. Is that something we need to be concerned about? No. But when you get into high duty seals like the SH, you definitely want to avoid this zone. If you also think of the SH and you look at the rotating seat, I should have had a graphic up here, but I don't. If you look at the rotating seat, we have a pin, a round pin that also goes into a hole, and those diameters are probably somewhere between these two. I would have to look at an exact design. I didn't have time to do that. My guess, it's probably somewhere around a 0.7 ratio. So you might get stresses that are maybe 2 or 3 times that of this ideal ratio. And again, that's okay because the pins and the holes in the face are adequately designed for that. A lot of the drive forces on the SH seat go through the O-ring, and then also a traction load between the back of the seal face and that lap support surface on the sleeve. A lot of people don't realize that, but that's a big component of the drive force. Not the pin. The pin's kind of there to get you started on startup, and then any sort of transients, it's nice to have that pin drive. And so that being said, even though you might have this larger ratio, maybe 0.6 or 0.7, and you're going to have a stress factor where you're maybe 2 or 3 times, given the rest of the drive support mechanism, you're going to be fine. But when you're looking at competitor seals, and I know I ask our engineers a lot of the time, anytime you see a competitor seal, save it somewhere and really study it. Study it for 15 or 30 minutes. Because as you look at it longer, things will kind of present themselves that you won't see on first glance. And this is one of them. So always be looking for these really high pin diameter to slot diameter, or even planar contact Hertz stresses when you're looking at our competitor seals. And when we talk about robust, a word that I hate because it has no meaning, what you can do is dive into features like this and talk about stress concentration factors, point stresses, Hertzian contact loads, and those sorts of things. All right, pretty cool topic. Thanks for calling in, and I'll talk to you tomorrow. Have a good day.